So 8.6 is going to be the last section of new material that we do all semester. And if I do a good job, it shouldn't be that hard of a section. So in this section, we're going to be graphing inequalities in 2 dimensions. You may have graphed something like the inequality x is less than 6 on a number line before. To do that, maybe you created a number line that had negative infinity on the far left edge, positive infinity on the far right edge, and then eventually you find 6 on there. And because I don't have an or equal to, you either put a round circle above the 6 or a round parentheses above the 6 and draw a line pointing towards the numbers that are less than 6, which are the numbers to the left of 6. This would be a number line representation of all the numbers on a number line that are less than 6. We're going to be asked in this section to do a 2-dimensional representation and list all the points who have x coordinates less than 6. And how do I do that? Well, first I draw a dashed vertical line through 6. This is kind of the equivalent of the round parentheses or open circle that you might do on a number line. All the points on the vertical line drawn through 6, if I draw them, if I wrote some points, which I don't really have to, each point on that line has an x coordinate of 6. They shouldn't be included in the graph of all the points on the graph whose coordinates are x is less than 6. The dashed line omits the points that have x coordinates equal to 6. So I drew a vertical dashed line to indicate the points that have x values of 6, dashed line saying they're not included. And then I shaded left as opposed to right, because each point to the left of this vertical line drawn through 6, regardless of what its y value is, its y value could be bigger than 6, its y value could be equal to 6. But every point to the left of this vertical line, if I only look at its x coordinate is a number that's strictly less than 6. Even if I butted right up to this line, maybe the point 5.99 comma -2, this point right here still fits the criteria that x is less than 6. So my shading only covers points whose x coordinates are less than 6, and any point that's not shaded, say like this point here, like the point 7.5, it's not shaded for a region. And the reason is any point that's not covered by the shading, its x coordinate is bigger than 7. So this is a picture of the graph in 2 dimensions, x is less than 6. In general, we're going to be asked to graph inequalities that have greater than signs, greater than or equal to signs, less than signs, and less than or equal to signs. If I have the x on the left-hand side and not a y, my equation will graph to be a vertical line. All inequalities that only have an x, if I'm graphing them in 2 dimensions, they're going to graph to be vertical lines. The type of line I'm going to get is going to be dependent on the inequality. If the inequality doesn't have an or equal to, I get a dashed line. If the inequality has an or equal to, I get a solid line. For shading, anytime I'm asked to graph an x with a greater than, I'm going to shade right. Anytime I'm asked to shade an x with a less than, I'm going to shade left. Let me show you what I mean by doing a couple problems from the homework. Problem 2 wants me to identify in a 2-dimensional graph the region where all the points whose x values are strictly greater than 5. To do this, I'm going to draw my x and y axes. I'm going to find 5 on the x-axis. And if I'm asked to draw an inequality with an x, I'm going to take the number that the x is compared to and draw a vertical line through that number. If I have an or equal to in my inequality, it would be a solid line. But in this problem too, I don't have an or equal to, so I'm going to draw a dashed line. So I'm going to find 5 on my x-axis, and I'm going to draw a vertical line. That's the line x equal to 5. Every point on this line has an x coordinate of 5. So this is the beginning of sketching my vertical line that represents all the points on the graph that have x coordinates strictly bigger than 5. So I'm going to start off and draw a dashed line through 5 on the x-axis. The reason I'm drawing a dashed line is because I don't have an r equal to, and any point that has an x-coordinate of 5 isn't supposed to be included in my answer. And now I have to shade, and for x's, if I have a greater than, I'm going to shade to the right, because on the x-axis, the numbers get bigger or greater than 5 as I go to the right. So my little chart on the screen right now is going to tell me the direction to shade, if it's not completely obvious. If I'm trying to cover up points whose x coordinates are bigger than 5, I'm going to shade to the right of 5. So let me just shade the best I can. I'm supposed to shade straight up to the line, but not actually cross the line. That's got to be more than good enough. This would be a reasonable picture of the inequality written in 2 dimensions, x is greater than 5. It includes any point to the right of the vertical line that goes through 5 on the x-axis. All these points, if I found any of the points in here, their x-coordinate would be bigger than 5 and need to be included in my answer. Any point on the dashed line has an x-coordinate of 5. It needs to be excluded from my answer. And any point to the left of the dashed line has an x-coordinate less than 5. It also needs to be excluded from my answer. In number 4, I'm asked to graph the points whose x-coordinates are either 5 or bigger. And to do this, I'm going to start off to draw a solid vertical line through -5 on the x-axis. That's going to identify the points who have x-coordinates equal to -5. And I do a solid vertical line as opposed to a dash because of the or equal to. So this actually includes all the points on the line whose x-coordinates are -5. After that, for x thens, greater thans, I shade right, less thans, I shade left. So this is another greater than, so I'm going to shade to the right and cover up every single point to the right of that vertical line. Then I will successfully identify all the points whose x-coordinates are equal to -5 on this line, and then I'm going to have identified all of the points whose x-coordinates are bigger than -5 by going to the right of this line. And then just shade however you want to shade. This is going to get ridiculous. I'm not going to get that intense with my shading. I'm just shading every point to the right of that vertical line as well as you want to shade or as poorly as you want to shade. It doesn't matter, just so I can tell which side of the line that you're shading. 6 asks me to graph the line x is less than 6. So to do that, I'm going to draw a dashed vertical line through 6 on the x-axis. Dashed because I don't have the or equal to. And this is kind of the boundary. All the points on that dashed vertical line have x-coordinates of 6. All the points to the right of that vertical line have x-coordinates that are bigger than 6. All the points to the left of that vertical line have x-coordinates that are less than 6. Because this is a less than, I'm going to shade to the left. And this is the way I can represent all of the points that have x-coordinates that are getting lazier and lazier, but it's okay. I'm just shading everything to the left of that line. This is the way that we would show in 2 dimensions all of the points that have x-coordinates less than 6. Any point on the line has an x-coordinate equal to 6. The dashed means I exclude that point. Any point to the right of the line has an x-coordinate bigger than 6. Those are all excluded because they're not covered by the graph. And any point to the left of the vertical line has x-coordinates less than 6. They're included in my work. For x is less than or equal to -1, hopefully you don't need me to do this. But to do this, I'm going to draw a solid vertical line through -1 on the x-axis. The reason the solid line is because I'm including the points that have an x-coordinate of -1. So there's my solid vertical line through -1 on the x-axis. And this is a left then, so I'm going to shade left. For x's, greater than shade right, less than shade left. And best I can, shade up to the line, as close as you can to the line without actually going over it. I can't get that close. And then shade everything to the left of that line, however tight you want to shade it, it doesn't matter. And that would be a two-dimensional graph of all the points whose x-coordinates are equal to -1 or less than -1. All the points on the line itself have x-coordinates equal to -1. All the points to the left of the line have x-coordinates less than -1. All the points to the right of the line have x-coordinates bigger than 1. The next kind of graph that we need to be able to deal with is graphs of inequalities that only have y's. And it's basically the same idea, other than I get horizontal lines and I go up and down as opposed to left and right. So if I was asked to graph an inequality that only has a y, equations that only have a y become horizontal lines. If I want to graph the line y is greater than or equal to -3, I'd start off by drawing a horizontal line solid through y equal to -3. And every point on that line, that solid horizontal line, is going to have, if I could actually write the point rightly, it's going to have a y coordinate of -3. Every point on that line, like this point right here, is a point 2, -3. Here's the point 0, -3. So that first line that I would draw, I draw it solid, which includes every point on the line. And every point on the line is included in my answer because the y coordinate is equal to -3. And then I need to shade. I need to shade for the y's are greater than -3. And if I go up from -3, the y's are bigger. Like here's the point 1, 4. If I just look at its y is bigger than -3. Here's the point -1, 2. Don't worry about the x, just look at the y is bigger than -3. So all the points that I shaded up over, the y's are bigger than -3. If I came down to like this point, -1, 5, its y is less than -3, so it doesn't get shaded on. So for y's, if equation only has a y, this is going to be my template. For greater thans, I'm going to shade up. For less thans, I'm going to shade down. And the same reason, we're going to do dashed and solid lines the same way. If you don't have the or equal to, you get a dashed line. If you have an or equal to, you get a solid line. So for problem 10, I'm going to draw a horizontal line, dashed, through 3 on the y-axis. And this would give me all the points on the graph whose y-coordinates are equal to 3. None of those are included in my answer because their y's are 3. They need to be ignored. But they separate the points of which the y's are bigger than 3 or the y's are less than 3. Because this is a greater than, I'm going to shade up. And when I'm shading up, every single point that I shade over, its y-coordinate is physically going to be bigger than 3. So it doesn't matter how you shade, I'm shading differently every time. doesn't matter. Just as long as you indicate that I'm trying to shade every point above the line, none of the points on the line, none of the points beneath the line. So I'd claim this is an acceptable graph for problem 10. It doesn't include any point on the line. Doesn't include like the point 2, 3 because it's y equals 3. Doesn't include like the point 5, 0 because its y is less than 3, but it includes every point above the line. It includes like the point 0.06. The reason it includes the point 0.06 is because its y is bigger than 6. Any point that I can draw in this pink area, if I wrote down both its x and its y is going to be bigger than 3. Any point beneath the shaded area, if I wrote down its y is going to be less than 3. And any point on the dashed line, its y is going to be equal to 3. The dashed line means I'm excluding those from my answer. To do problem 12, I'm going to start off and draw a horizontal line through -6 on the y-axis. And it's going to be solid because of the or equal to. This horizontal line that goes through -6 on the y-axis represents every point on the graph who has a y-coordinate equal to -6. So this satisfies the picture of y equal to -6. To it, I need to add the points whose y-coordinates are greater than -6. And if I have a greater than or equal to, I'm going to shade up with a solid line. So best I can, which is not so great. This would be somewhat of a picture of all the points on the graph whose y-coordinates are either equal to -6 or greater than -6. Problem 14 wants me to graph all the points whose y-coordinates are strictly less than -1. So I'm going to start off, look at my template here. For a y less than, I'm going to draw a dashed line and shade down. So I'll find -1 on my y-axis, draw a dashed horizontal line through it so it excludes from my answer any point whose y is equal to -1. That's all the points on this line have a y equal to -1. So I'm not including the boundary, but I'm including all the points under the boundary because if you go beneath this line, the y's are going to be less than -1. Above this line, the y's are bigger than -1. So I'm just going to shade now the appropriate side of the line. And the appropriate side of the line is beneath the line. Some students do such beautiful shadings. Not me. It doesn't matter. It doesn't need to be a work of art. Y is less than or equal to 0. I'm going to plot a solid line through 0 on the y-axis. I get a solid line because of the or equal to. Because of the less than, I'm going to shade down. 0 is a number I don't always show. I see 1 through 9 and -1 through -9 on my y-axis. 0 on my y-axis is at the origin. So for my solid line that I need to draw, it's kind of already drawn for me. That is the equation of the x-axis. So there's my solid line through 0 on the y-axis, solid because of the or equal to, and now I'm going to shade down. Supposed to shade everything all the way up to the line, and I just kind of do the best you can. I will, believe that you understand the shading if you do something even as crude as this. So those are the easy kinds of shadings. If I have an equation that only has an x or only has a y, I get vertical lines or horizontal lines, and the shading is intuitive. Once I start getting inequalities that have both x and y's, then it's not as intuitive. So let me try to walk you through what we're going to do if we're asked to graph an inequality that only has both an x and a y, so it's a slanted line. I wrote some steps down. and I'll try to walk you through the steps with this example. I'm going to graph x plus y is less than 6. So what do? To get started, to graph an inequality that has both an x and a y, find the x-intercept and find the y-intercept with the problem changed to an equal sign. So temporarily, I'm going to change the inequality to an equal sign to find the intercepts, only on step 1, and then I'll go back to the inequality symbol. So I'm going to change the inequality symbol to an equal sign only for step 1, find the x-intercept by letting y equal to 0. So I plug into my x plus y equal to 6, I plug in 0 for y. The algebra gives me x equal to 6. That gives me 6, 0 for my x-intercept. Do the same thing with this for the y-intercept. For the x plus y equal to 6, which is the modified equation for finding intercepts, plug 0 in for x. That gives me 0 plus y equal to 6. That's going to give me y equal to 6. That represents the point 0.06. So that's the beginning of my steps. I found the x and the y intercepts. Now I'm going to plot them. I plot at the point 0.06 and I plot at the point 60. Just like for the x's and the y's, if I had an or equal to, I would make a solid line. Because I don't have an or equal to, I get a dashed line. So I plotted the points, the intercepts, and I connected them with a dashed line because I had a less than. I would connect them with a solid line if I had an or equal to. So the reason the line isn't drawn is because every point on the line, like here's the point 42, here's the point 33, every point on the line, if you added up its x and its y, if you took the point 0.06 and you did 0 plus 6, its y is going to equal to 6, which isn't less than 6. The point 33, its 2 points, if you add them up, their x and y add up to 6. Every point on the line, if you add its x and y up, it specifically equals 6. This is why this is the boundary. All the points on the line, if you add the x plus y, they equal to 6. Those don't need to be included. But on one side of the line, if I take any point and add its x and y coordinate, they'll be less than 6. And on the opposite side of the line, if I take any point and add its x and y coordinate, they'll add up to more than 6. So now I need to figure out how to shade. And what I generally do to figure out the side of the line that I'm shading is I pick 2 points on the x-axis on either side of the x-intercept. So the x-intercept is sitting here at the point 60, and right to the left of the x-intercept is the point 50. Directly to the right of the x-intercept is the point 70. What am I going to do with those? I'm going to take each one of those and plug it into the original inequality and tell myself whether I get a true or false statement and help me figure out how to shade. That's what I did on the next page. So I picked the point 50 and the point 70 because they are on opposite sides of the x-intercept. The point 50 is directly to the left of the x-intercept. The point 70 is directly to the right of the x-intercept. Now for each one of these, I'm going to take the x and the y and plug it into the original problem, x plus y is less than 6. So for the 50, I plug in 5 plus 0 is less than 6, and I get 5 is less than 6. For the point 70, I plug 7 in for x, 0 in for y, and get 7 plus 0 is less than 6, which is 7 is less than 6. So I evaluate the points in the original function, and then I ask myself, do I have a true statement or a false statement? The first statement in the top row, 5 is definitely less than 6, so I write true next to it. The next statement, 7 is not less than 6, 7 is bigger than 6, so that's a false statement. My shading needs to cover the point that produced a true result, and it can't cover any point on the line that doesn't have a true result. So when I went and shaded this using Desmos, my shading covers all these points. As a matter of fact, on Desmos, I just typed this in on Desmos, which is a wonderful computer program, and it just did this for me, and I added the intercepts. So any point in the shaded area, if you look at any point, like the point 0, 3, if you add its x and you add its y, you're going to get a number less than 6. Any point not in the shaded region, like the point 5, 6, if you add its x and you add its y, you're going to get a number bigger than 6. The reason we shade down is because every point beneath this dashed line satisfies. If I add its x coordinate and its y coordinate, I get a number less than 6. No matter which point I pick in this shaded region, they all make this statement true. And no matter which point I pick in the unshaded region, if I put the x and the y in, they make the inequality false. So let's do a couple shadings or works, and better do number 17 because I just did it, 18. So for 17, step 1, I'm going to change the inequality symbol to an equal and find the x and the y intercepts. Only temporarily do I use an equals. So step 1, for algebra purposes, change the inequality symbol to an equal sign only for step 1. Find the x-intercept. To find the x-intercept, I let y be 0. So I'm going to go x plus 0 equals to 8. That's going to give me x equal to 8. And in terms of an intercept, that's the point 8, 0. Next, I'm going to find the y-intercept by going 0 plus y equals to 8, and I'll get y equal to 8. That represents the point 0, 8. So on my y-axis, I'm going to mark the point 0, 8. On my x-axis, I'm going to mark the point 8, 0. Now I'm going to connect the points. I'm done with step 1. I've found the x-intercepts. I'm moving on to step 2, which is to plot the x-intercepts and connect them appropriately. Here I get a dashed line because I don't have the or equal to. Done with step 2. Now for step 3, I'm going to do this kind of business right here. I'm going to do a little table, and I'm going to pick 2 points. One to the left of the x-intercept, which is the point 7, 0. One to the right of the x-intercept, which is 9, 0. So my points are going to be 7, 0 and 9, 0. They're directly on either side of the x-intercept. And now I'm going to evaluate into x plus y is less than 8. So I'm going to go 7 plus 0 is less than 8, putting 7 in for x and 0 in for y. That gives me 7 is less than 8. And the next one, I'm going to go 9 plus 0 is less than 8. This gives me 9 is less than 8. And then I'm going to do a true or false statement. 7 is definitely less than 8, so that's a true. 9 is bigger than 8, so this statement is false. I'm going to shade over the true point and not shade over the false point. So for shading purposes, I need to shade right up to the line, and I need to shade the side of the line that contains the true point 7, 0. So I'm going to shade right up to the line and everything under the line. So this would be how this would shade. This would be a picture of all the points that their x plus y is less than but not equal to 8. Move on to 20. Eventually we're going to have to go into a part 2. So for problem 20, step 1, change the inequality to an equal sign. Find the x and the y intercepts. So I'm going to go 4x plus 3y equals 12. Go for the x-intercept. Do 4x plus 3 times 0 equals 12. The 0 piece will go away. This will give me 4x equal to 12. And when I divide, I'd get x equal to 3. That's going to represent the point 3, 0 for the x-intercept. And then I'll go for the y-intercept and do 4 times 0 plus 3 times y equals 12. The 0 piece will go away and leave me with 3y equals to 12. I'll divide by 3 and get y equal to 4. For a lot of these, you can get the intercepts in your head. So I'm going to plot now onto step 2, the point 30 and the point 04. I'm going to connect them with a dashed line because I don't have the or equal to. So I'm into step 2, plot the x-intercepts, connect them with the appropriate line, solid if you have the or equal to, dashed if you don't, and now I'm going to go for shading purposes. What I'm going to do is I'm going to pick a point on either side of the x-intercept. This is overkill. You can do less than this, but I've had success doing this. So the points I'm going to pick are the point 20 and the point 40. 20 is right to the left of the x-intercept, 40 is right to the right of the x-intercept, and then I'm going to evaluate into 4x plus 3y is greater than 12. So in the original problem, plug in 4 for x, or 2 for x, 0 for y. This gives me the statement 8 is greater than 12. And then for the point 40, I'll do the same. I'll do 4 times 4 plus 3 times 0 is greater than 12. And this will simplify to 16 is bigger than 12. And then I ask myself, true or false? The first one, 8 isn't bigger than 12. 8 is less than 12. So that's false. The second one, 16 is bigger than 12. That's true. So I should not cover the point 20 with my shading. I should cover the point 80 with my shading. So I'm going to cover with shading the point 80, or the point 40. The point 40 is above the line. So here I need to shade above the line. So everything above the line will make the inequality true. Let me just do 2 more and make this video longer than I want to, but it will fit better. So 22, I'm going to start off and find the x-intercept of 3x minus 2y equal to negative 6, and then the y-intercept of this. For x-intercept, I let y be 0. I'll go 3x minus 2 times 0 equals negative 6. This gives me 3x equals negative 6, x equals negative 2. That will graph out as the point negative 2 comma 0. For the y-intercept, I do 3 times 0 minus 2y equals negative 6. The 0 piece goes away. I get minus 2y equal to negative 6. Divide by negative 2, divide by negative 2, and get y equal to 3. The y-intercept is going to be the point 0,3. So I plot the point negative 2, 0 and the point 0,3, and I draw them with a solid line. I don't have to write the coordinates down. I just have to make the dots and get the right kind of line. I get a solid line because of the or equal to. Now for my shading, I'll take my point that I want to check, and I want to point to the left of the x-intercept. I'm going to do negative 3, 0, which is to the left of the x-intercept, and then negative 1, 0, which is the point directly to the right of the x-intercept. And then I'm going to evaluate. I'm going to plug in to the top equation, or into the original equation, negative 3 for x and 0 for y. And this is going to simplify to negative 9 is smaller than negative 6. And then for the bottom one, I'm going to plug negative 1 in for x and 0 in for y. So 3 times negative 1 minus 2 times 0 is less than or equal to negative 6. This gives me negative 3 is less than or equal to negative 6. Now I ask myself which one is true, which one is false. Negative 9 is smaller than negative 6. Here's negative 6, there's negative 9. Negative 9 is to the left of it. This is true. Negative 3 is not less than negative 6. Negative 3 is to the right of negative 6. This is false. So for my shading, I need to cover the point negative 3, 0 and not cover the point negative 1, 0. So as I go to shade, I need to cover the true point. The true point is negative 3, 0, which is right there. So I'm going to shade the whole north side of the line. That's 35 minutes. I had one more problem with this kind that I wanted to do, but I think we'd be good without doing it rather than making the video go past 36 minutes. So I'm going to pause. We're going to do a part 2, and I'm going to pick up with problem 26 and skip on that problem 24.